Quantifire. Eurocode Critical Temperature Calculator. In this video you will learn about how to use the Eurocode calculator to determine critical temperatures relative to specified loading criteria. This will include beams, columns, and tension members. You will also learn how to enter exact loads, ultimate limit state utilization and utilization at the accidental limit state of fire. The calculator should only be used by a competent person. Any estimate that uses this approach should always confirm that the Eurocodes are considered acceptable on the project, clarify all inputs to the project design team including any conservative assumptions, and ensure that the structural engineer is in agreement together with the approving authority and any associated stakeholders. After logging in, you will see your permissions relating to the T-Crit calculator. In order to use it you must be using a Quantifire Plus license version of the software and be authorized to use the module by your appointed administrator. Let's start with beams. We will enter a four-sided 5332 10 by 122 beam with a length of 7.5 meters. Let's insert the section, but we will set the temperature to use the advanced T-Crit calculator. The temperature shows as 541 degrees Celsius. Quantifire has a number of default settings for the advanced critical temperature calculator. When the section is inserted, these are used as part of the calculation. Let's look at them a bit more closely. Click on the main menu and then the Edit Advanced Settings. These are typically conservative defaults. Users are advised to review and familiarize themselves with these settings before starting a project. By default, all members are stressed to 65% utilization at the fire limit state in line with recommended guidance in the Eurocode. For composite beams, a slab depth of 120 mm is assumed together with a re-entrant profile deck. You can use the T-Crit editor button to look at the beam and its calculation a little more closely. This button can be used for any section, including those that have been entered using a default or user-set temperature. However, it is only for use with typical I sections and hollows. We can now see the calculator in full. The section designation is displayed at the top. White boxes can be modified by the user and are automatically populated with the default values. We are going to consider the scenario of assessing a beam when the exact loading conditions are known. Let's change the steel grade to B275 and set the partial safety factor for fire to be that for an office to the UK National Annex. The spacing of adjacent beams, by default, is span upon 4. Let's set the spacing as known at 7.5 meters. Now let's specify a known loading scenario of 5 kN per square meter for dead loads including the self-weights, and 3.3 kN per square meter for the imposed load. When we click Assess Beam, we can see that the beam has been stressed at ultimate limit state to 73% and has a critical temperature of 623 degrees Celsius. Clicking on Generate Report allows us to see a summary of the calculation. We can verify the beam geometry and can check the applied moment at ambient and at fire. We can also see the capacity of the beam at ambient and a summary of the strength of the beam at the critical temperature. Now let's consider the same scenario, but let's assume that the structural engineer hasn't given us the exact loading. Instead, we are told that the ULS utilization is 73% and that the dead-to-live load split is approximately 60-40. We will select that the loads are unknown and to use a ULS utilization. We will set the utilization to be 73% and enter 60% as the dead load proportion. Clicking on Assess Beam shows a failure temperature of 623 degrees Celsius. That's the same temperature as before. Quantifire has determined what dead and live load, together with their respective safety factors, will give a ULS load combination utilization of 73%. The values associated with this are given in the structural report. From the report we can infer that the utilization at the accidental limit state of fire is the bending moment in fire divided by the section's ambient capacity, i.e. 350 divided by 846. This gives approximately 41%. What if the structural engineer has provided fire limit state utilizations? In other words, they have run a fire load combination in their structural model and are able to provide these directly. We will again select that the loads are unknown and that we are considering accidental limit state of fire utilization. If we enter 41% and then click on Assess Beam, then the temperature is shown as 624 degrees Celsius. This is 1 degree Celsius more than previously, but it's due to us rounding the utilization to an integer of 41. We considered the 3 different loading methods within Quantifire. The same load inputs are also applicable to columns and tension members. For this beam, let's click Accept and return to update the MTO Builder page. The temperature is now updated and the product thickness re-evaluated. There are often times when no loading information is given at all. The calculator can still be used, but conservatism and care should be taken. Let's review this, using the same beam, but now we'll say that it is a non-composite 3-sided beam supporting concrete. Common approaches are to retain the 65% utilization in fire, or perhaps even to increase it to 70% for storage occupancies, although this can be very conservative. Alternative approaches may include working at ULS and setting the member at 100% utilization, assume a 50-50 split of dead to live load, and use an appropriate partial factor for imposed load in fire, for example, office occupancy. Whatever approach is adopted, be sure to inform the end user and the project's structural engineer of any assumptions. Quantifire's technical basis schedule report should ideally be provided in all instances. Many beams act in. Let's reset the default T-crit settings. Many beams act in composite with the concrete slab. Let's consider a 406178 by 60 UB, and we will denote it as composite by ticking the checkbox. Be aware that in the previous non-composite example, we could have made it composite by setting this drop-down input to be yes. We can now see the inputs associated with the steel deck and the concrete slab. Again, these are populated from the default settings and can be modified by the user. Interrogating the structural report shows us how the temperature is being treated over the cross-section. Quantifire assumes an unprotected beam and heats the web and flanges with respect to the standard fire, until a structural failure occurs. Here we can see that the top flange is at 491 degrees Celsius, and the web and bottom flange are at 565 degrees Celsius. EN 1994-1-2 permits the web temperature to be the same as the bottom flange when the beam's overall depth does not exceed 500 mm. The structural checks take into consideration the overall section profile, which includes the capacity of the elemental parts of the steel section, the shear studs and the concrete. In this case, the critical temperature is the bottom flange value of 565 degrees Celsius. Now let's consider columns. We will use a 203-203-60 column with a height of 4 meters. This gives a temperature of 450 degrees Celsius. Let's look at it a bit more closely. Columns are treated as acting under pure compression, and their critical temperatures are a function of their section size, the grade of steel and their height in fire. The default steel grade is set at S235 as this is common in Europe. If we change this to S355 and assess the column, we see the temperature is now 472 degrees Celsius, with failure associated with flexural buckling about the weaker axis. By default, columns are assumed to not be located within a braced frame structure. This is a conservative position. However, many common structures are braced frame designs, i.e. they are designed to withstand lateral forces such as wind. Let's say the column is in a braced frame and is at an intermediate story location. These two changes now result in a temperature of 590 degrees Celsius. Adopting inputs like these should always be verified with the project's structural engineer. Let's accept this and return to the estimate. Users should be aware of column compression calculations for hollow sections when using the default settings. The common European column temperature of 500 degrees Celsius is based on an empirical value, not an analytical calculation. In other words, it is entirely possible to determine temperatures lower than 500 degrees Celsius. As an example, let's insert a 140 square section with an 8 mm wall thickness. The default settings give a temperature of 212 degrees Celsius, which for our product, is too low with respect to the certified limits. Now let's consider a tension member. We'll insert a round rod with a diameter of 80 mm. The temperature with the default settings gives 541 degrees Celsius. Members subject to tensile loading are relatively straightforward. Their critical temperature is purely a function of the load applied, which can be defined in the same manner as beams and columns. For this example, let's assume the rod is fully utilized at ULS, has a 50-50 split of dead to live load, and is subject to a congregational occupancy type with the base Eurocode. The resultant temperature is 570 degrees Celsius. We've seen how individual sections can be assessed, but the real benefit comes when working on large projects. We'll now look at applying T-crit assessments across all sections. On the screen, we've loaded a full project which is based on a single temperature of 500 degrees Celsius. We have 71 sections which require approximately 46,000 liters of product. If we were looking to optimize this, we could be selective as to which sections we want to consider. For example, looking at the project statistics on this job tells us that section IDs 30 and 40 account for around 33% of the surface area. We could focus only on those sections to simplify our efforts. For example, we may request from the structural engineer the worst-case utilizations for those members. Alternatively, and in the interests of application productivity, we could focus on section IDs 3 and 15 since these are the only two sections that require 3 coats of product. For now though, let's look at the project as a whole. Let's consider the default settings. The structural engineer has confirmed that all sections use grade S355 steel. They also tell us that in the absence of fire limit utilizations, they are happy for us to assume an ambient ULS utilization of 100% and an office occupancy to the UK National Annex. Finally, they have confirmed that columns are all in a braced frame design and can be considered as intermediate story locations. Using the Change All button, let's modify the critical temperature. Select the method to be advanced, and tick the checkbox to use the default settings. When we click Apply Changes, Quantifire does a full Eurocode calculation for each member, displays the resultant temperature and determines the new product thickness. The project now requires 35,500 litres, or rather a saving of around 22% over the initial assumed 500 degrees Celsius temperature. Had the original steel list included specific utilizations, then these could have been imported via the canvas and the temperatures evaluated directly. This concludes the critical temperature calculator tutorial. We hope that it's provided you with an overview of how to apply it on projects. Full information is given in the Quantifire user guide. Look out for related topics in other training videos, including the bulk importability, cellular beam assessments and automated structural fire optimization.